Picture yourself, age 6, holding a fat paper dictionary. Your teacher says, find the word octopus. You don't start at aardvark and read every page until you hit O. Nobody taught you a method, but you flip somewhere past the middle, glance at the top of the page, see you've landed on tornado, and flip back. Then forward a bit, then back a tiny bit. In maybe 7 flips, you've got it. Here's the strange part. A computer scientist would look at what you just did and say, congratulations, you ran an O log n algorithm. You've been doing it since first grade and nobody ever told you it had a name. Let's slow this down. The dictionary has, say, 2,000 pages. If you flipped one page at a time from the front, in the worst case, you'd flip 2,000 times. That's the brute force way, what computer scientists call linear search. But you didn't do that. You opened to roughly the middle, page 1,000. You saw the letter TT comes after O, so instantly, without thinking, you eliminated pages 1,000 through 2,000. Half the book, gone. One flip, half the problem destroyed. That single move is the entire trick we're going to unpack today. Now you're staring at pages 1 to 1,000. You flip to the middle of that is page 500. You land on letter F. F comes before O, so you eliminate the front half. Pages 500 to 1,000 are what's left. Then you do it again. Page 750, letter M, still too early. Now you're between 750 and 1,000. Notice the pattern? Every flip, the search space gets cut in half, not by a little, by half. And halving is a ruthless operation. It shrinks problems at a speed that feels almost magical when you write it down. So how many flips does it actually take? Start with 2,000 pages, halve it, 1,000, halve again, 500. Then 250, 125, 62, 31, 15, 7, 3, 1. Count those steps. 11 from 2,000 pages down to 1 in 11 flips. Compare that to linear search's worst case of 2,000. You've done the same job roughly 180 times faster. And here's the punchline. If the dictionary were 10 times bigger, basically 20,000 pages, you wouldn't need 10 times the flips. You'd need about 4 more, 14 total. That's the soul of logarithmic time. This is what the notation O log n actually means, stripped of math anxiety. The n is the size of your problem, pages, names, songs, whatever. Log n means, how many times do you have to cut n in half to reach one? For 1,000 items, about 10. For 1,000,000, about 20. For 1,000,000,000 items, every human alive, about 30. 30 steps to find one specific person in a sorted list of everyone on Earth. That's not a clever trick. That's the universe rewarding you enormously for one property, the data being sorted. And that sorted requirement is the whole game. Binary search only works because the dictionary is in alphabetical order. When you open to page 1,000 and see tornado, you know with certainty that octopus is to the left. Not probably, certainly. Order is information. Every page in a sorted book is whispering a hint about every other page. In an unsorted book, that whisper is gone. You'd be back to flipping one page at a time because seeing tornado tells you nothing about where octopus might hide. Sorting is the price you pay up front to make every future lookup absurdly cheap. Once you see this pattern, you start finding it everywhere. Think about the last time you played a guessing game. I'm thinking of a number between 1 and 100. A child guesses 50, you say higher, they guess 75. Lower, 62, higher. That child is doing binary search perfectly with zero training. They're not guessing randomly. They're cutting the range in half each time because they intuitively know halving is the fastest way to corner an unknown. The whole game is solvable in at most 7 guesses. Try it. You won't need more. Or think about debugging code. You've got a program that worked yesterday and broke today. You made 40 commits in between. How do you find the one that broke it? You don't reread all 40. You check the commit in the middle. If it works, the bug is in the second half. If it's broken, it's in the first half. Git even has a built-in command for this called git bisect, and bisect literally means cut in half. Programmers debug by binary search every single day, and many of them don't consciously realize that's what they're doing. Here's a stranger example. A piano tuner adjusts a string by ear. They pluck it, too sharp. They loosen, big turn. Pluck, too flat. They tighten, but a smaller turn this time. Pluck, slightly sharp. Even smaller turn the other way. Each adjustment is roughly half the size of the last because they've bracketed the correct pitch between their previous attempts. That's binary search, executed not on a list but on a continuous range of frequencies. The same algorithm your 6-year-old self ran on a dictionary is what a tuner runs on a piano string, and what a chef runs when seasoning a soup. Taste, adjust, each correction smaller than the last. Even your eyes do something like this. When you scan a bookshelf for a specific title, you don't read every spine. You glance at the middle, recognize the general section, jump toward where you expect the book to be, then make smaller saccades to zero in. Your visual system is constantly bracketing and halving. Evolution didn't read a computer science textbook. It just discovered, the same way human programmers did in the 1940s, that when information is structured, sorted, ordered, ranked, halving is the cheapest way to find anything. Now let's flip the question. Why doesn't this trick work everywhere? Why can't Google search the web in 30 steps? Because the web isn't sorted on the thing you're searching for. You type best ramen near me. There's no alphabetical order of restaurants by deliciousness. Google has to do enormous prep work, building indexes, ranking, pre-computing, so that at query time, something about your search becomes binary search-shaped. The lesson generalizes. Anytime you want fast lookup, you pay for it by imposing structure beforehand. Sorting the dictionary takes effort, but you only sort it once, and then every kid for 100 years gets login lookups for free. So here's the aha moment I want you to leave with. Binary search isn't really an algorithm about dictionaries or numbers or code. It's a principle about information. Every time you have a problem with one confident decision, you're doing the most efficient possible thing a searcher can do when the world gives you ordered hints. You've been doing it since you were 6. The piano tuner does it by ear. The debugger does it by commit. Your eyes do it on a bookshelf. The next time someone tells you an algorithm sounds intimidating, remember? You ran one before you could ride a bike. The math just caught up to what your brain already knew.